Hello, and welcome to the Lund University International Podcast. On the show, you'll hear from current students, alumni, researchers, professors, and many more special guests as we explore what it's really like to live, study, and work at Lund University, a world top 100 university. My name is Fabio, and I come from Napoli, Italy. I've been studying here in Lund for 4 years, done my bachelor's, and I'm currently a master's student in European Affairs. Today, we're focusing on the life of an international researcher in Sweden. We're joined by a brilliant mind who came to Lund to pursue his PhD in quantum physics. We'll talk about his journey, including what brought him to Lund, the best and most challenging parts of completing a PhD here as an international researcher, and how Lund's research environment stacks up globally. Of course, we'll also explore his cutting-edge work, from the curiosity that led him to quantum entanglement and Schrödinger's cat, to what his discoveries might mean for our everyday lives in the coming years. Welcome to Gabriele.
Thank you very much, Fabio.
So can you tell us a bit about yourself? Where are you from and what's your journey?
So I am doing a PhD here in Sweden. I started more or less 2 years ago in March 2023. And I'm originally from Italy, actually from southern Italy, in Naples. And it has been a big jump so far, like from Naples to Sweden. So
So what brought you here, actually? What brought you to first choose Sweden?
Yeah, actually, it was quite by chance. So I was studying for my master's thesis, and I knew that I wanted to do a PhD. And, like when you want to apply for PhD, you just start looking for open positions online. And I found this position actually by chance, just by Googling. And, it's like I knew that Lund University was a renowned university, but I also liked a lot like the supervisor research and the supervisor as a person. So, like I did the application process and all the stuff. And here I am now. It's
we're glad to have you here in Lund.
Yeah.
And what did you study before? What's your journey, academic journey?
Actually, I did a bachelor and a master in physics. So the bachelor was in general physics, and the master instead I specialized more on theoretical physics. I studied in northern Italy, actually, at the University of Modena. Before, like now, my PhD is more focusing on quantum physics. Before, I was more on the theoretical particle physics side, and it's like I wanted to switch already when I was studying during my master, and actually, I finally had the opportunity here coming to Lund.
That's great. Those are some really interesting topics. I think we'll get to your research in a bit. But now I want to ask how is doing a PhD here in Lund? Can you tell us a bit about what has been your experience so far in these 2 years?
Yeah, I mean, I think that Lund University is quite good for doing a PhD for research, because compared to the other universities that I have studied in, it's like Lund offers a lot of possible activities, okay, as a researcher. It's like there is a lot of funding for research, so that you have the possibility to travel a lot and to interact a lot with international researchers. There is a lot of events and conferences going on, so that you can always meet up with new people. And from the research point of view, this is very, very important, because like the basics of research, there is the interaction with other researchers. So it's important to have the possibility to do this kind of stuff.
There's a lot of networking.
Yeah, it's a lot of networking, yes. And I think it's just because Sweden in general is pushing a lot towards research. This is something that it's not usual for all the countries, as we all know.
Yeah.
And so it's nice. I mean, in Sweden, and particularly in Lund, there is a lot of push on that side. And for a PhD student, this is quite helpful, yes.
And is your work more theory-based or a bit more practical?
No, I am a theoretician, so for me it's just math and coding. I think last time I entered a lab, an experimental lab, was I think 5 years ago. Okay. It's better to stay away from that, otherwise I will break something.
And tell us what have been your highlights for the past couple of years? How long are you gonna do your PhD for? Actually, 3-4 years?
Yeah, I mean, the time for the PhD is 4 years. Then most of the PhDs in Lund work in this way. It's like you have this fixed contract of 4 years, and then you have the possibility to teach, doing teaching assistance for different courses, and this gives you the possibility to have an extension to the contract. So like in general, it's up to 4 years and 6 months, more or less. So now I have done like almost 3 years. I have another year and a half still there. So yeah, it's quite a
you've been going through a lot of your PhD life.
Yeah, a lot. So that's true. I mean, there is like life as a PhD student is more like life that you live at university in your office. For me, it's in my office, and you just do research. So it's a lot of interacting with students, with professors. It's a lot of talking, and for me, staring at whiteboards, waiting for something to work.
Actually, one more question I have is actually that at Lund University, a PhD student is actually a teacher in some cases, right?
Yes, you do teaching assistant. So this means that, for most of the times, for most of the courses, you are the responsible for lab activities or exercise sessions. So there are the main teaching sessions, like the lectures that are held by the professor, and then PhD students are the responsible for these side activities that are quite useful to pass the exam, because like you have someone to interact with, so students can ask you questions about the lectures, about the exercises. It's important for them because like they get a lot of help in this way to, a guidance through passing to the study for passing.
Yeah, from someone who's very young as well, someone who's almost their age.
Yeah, this is a nice thing, because usually this is actually something very positive in Sweden. It's like in Sweden there is no hierarchy. Okay, it's like, so I have seen that students talk to professors in a very like chill and relaxed way. That's something that doesn't happen, for example, in Italy. But it's a positive thing to have teaching assistants, because exactly it's like we are more or less the same age. It's like it has not been so long ago that I was also studying for the exams. So it's good for them. I can give them some advice, and they are not scared or fear to ask stupid questions.
I completely agree. And so I've also graduated not long ago, and I really, really like the part that it makes you feel more relaxed, and definitely there's less of that pressure when you speak to like a professor, and like you're even scared sometimes in other places. Like when I've studied, for example, in Italy, you're a bit scared even to interact with the professor, but here it feels more easy, definitely.
Yeah, the situation is way, way different.
And you benefit from as a student.
And also as a researcher, actually, also as a PhD student, because it's also easier for us to go to a professor and ask a stupid question, because
that's true, because you're a student.
Yeah, exactly. In the end, I was just training to become a researcher, so hopefully, but it's like, it's nice to have a research environment that is quite relaxed. So.
And talking about research, can you tell us a bit more about your topic?
So far, like the research for my PhD has been focusing on the foundational aspects of quantum mechanics. And in particular, like I have been studying two of the main characteristics that if we want to make quantum mechanics, quantum physics, so different from the classical physics we are used to, so different from the physics that we study at high school, for example. So these two aspects are quantum superposition and quantum entanglement. So like through these years, these have been my main topics of research. Actually.
And tell us, what is the main difference then between physics that we all know about, we've all studied, and then quantum physics?
Yeah, it's like, there is no idea. It's like quantum physics is actually a branch of physics. So
okay.
It's just if we want to give a very naive definition of what quantum mechanics is, we can just say that it's a mathematical theory. It's a physical theory that wants to describe the microscopic world. Why do we need this? Because if we imagine that we take like, a huge magnifying glass and we look at the subatomic worlds like electrons, protons, neutrons, and all this stuff, and we see that they behave in a way that is different from what we are used to see in our everyday life for macroscopic objects. And probably one of the key characteristics of this weird behavior is exactly the quantum superposition that I've been studying. To explain quantum superposition, I like to oversimplify things so that they become...
Please, I'm a social scientist.
So I try to make them very simple. So it's like from a physics perspective, if you want to study an object is actually characterized by a set of physical properties, okay? So like I'm using this microphone. This microphone is a physical object, and it's characterized by a mass, by a density, by color, so it's black, and so on. Now, what is the main difference between macroscopic classical physics and quantum physics is that the objects, the microscopic objects in the quantum world, have not a fixed value of these physical properties. So let's imagine a world in which an object is just characterized by one property, the color, for example, and it has only two possible colors, like yellow and green, okay? Then what we are used to see in our everyday life is that if we have a macroscopic object, this macroscopic object has a fixed color. So either we see it yellow or we see it green. That's it. Instead, if you go to the quantum world, so if you want to go to the microscopic world, then you see that microscopic objects don't have this property. So the objects are not just either green or yellow, but they live in this continuous superposition of green and yellow. So if we want to be naive, we can say that they are at the same time both green and yellow until we don't look at them. When we look at them, then there is the so-called collapse of the state, and so the particle or the quantum objects becomes either green or...
Okay, I see what you mean. So you're going, physics is what we can observe.
Yes, exactly.
And quantum physics is what's deep inside.
It's what we can observe about the microscopic world.
Okay, definitely. That is super interesting. How did you get first interested in this?
Yeah, that's always by chance, actually. I was quite young. I was, I think, 15. I was in high school. And I remember that it was before Christmas holidays that my science teacher, you know how it happens, no? It's like you have to go for holidays and then the teacher always tells you, you should read these books so that you don't lose like interest and all these things. And he suggested us some popular science books on biology, evolution, these things. So I read those books and I liked them a lot. And like the next year I went to him and I said, look, I really like those books. Do you have other suggestions to me? And he looked at me and he said like, do you know what quantum mechanics is? And at that time I didn't even know what physics was. So I was like, no, I have no idea. So I could read this book. I think you could like it. And he was right. I mean, I still remember this book. It was like called Quantum Physics for Poets. And I mean, the main idea was that the two authors wanted to describe these physics phenomena, these weird physics phenomena, with the least amount of equation possible. So like for poets, no, for people that are not used to see math. And I read that book. I really liked it. And after that, I started reading other popular science books on quantum mechanics. Then, I started exploring and going towards general relativity, math. So I start to get hyped on it. It became more or less my hobby during high school. And then after high school, even if I was a little bit scared by the possible difficulties related to the math, because it's not an easy path, I decided to enroll in a physics program.
Because that's, but now that you've been telling me a bit about quantum physics, it doesn't look so foreign to me anymore. Like I'm getting it. Getting the particles, like the microscopic world, and until you look at it, you don't know, right? And that brings back to Schrödinger's cat, is it? That is the idea. Until you open the box, you don't know if the cat is alive or not.
Exactly. Yeah. I mean, the Schrödinger's cat is because you actually told it. You said, I'm starting to get it. No, because I told you that if you go to microscopic world and you see microscopic particles, they are in a superposition. They are both at the same time. They are green and yellow, and you just accepted it. No, because a particle is something that is very abstract. We are not used to see in our everyday life. And the Schrödinger's cat paradox is actually a way to make you understand that. Wait, do you really accept that reality works like that? Because Schrödinger, that was one of the father of the quantum theory, himself, he couldn't really accept it. Right? And he used this paradox to make people understand that what they were accepting about particles was quite weird. Because, there are different ways of explaining how the Schrödinger's cat paradox works. The easiest way, I think, is just to you take a box, you take a quantum object, a particle, and then you know that this particle is in a superposition of yellow and green. And this is something that I already sold you and you believe in it. Mm-hmm. Okay. And then in the same box, you put a bottle of poison and a mechanism that relates the particle and the bottle of poison. So this mechanism is just something that looks at the color. If it finds the particle to be green, breaks the bottle. If it finds the particle to be yellow, does nothing. And then in the box, you also put a cat that is a macroscopic object, actually is
something visible.
Something visible, something that you can touch, that moves as alive. And then you close the box. And then Schrödinger says, well, you bought the idea that a particle lives at the same time in this superposition of yellow and green, so it's at the same time yellow and green. But if you accept that, then you have to accept that now this system is constructed in such a way that if you accept that the particle is at the same time yellow and green, and then also the cat is at the same time alive and dead, because like the life of the cat is strictly connected to the particle. And I mean...
So what is your relation with objectivity? Like, is there an objective...
I mean, that's we are going into philosophy now. There is there is this way of saying in quantum physics that is just shut up and calculate, no? Because when you go into these weird aspects of physics, like this superposition of like cats that are dead alive at the same time, so you can go a little bit too much into philosophy, and so
that's what I'm thinking. There is a connection there.
Yeah, because there are many different ways of interpreting these ideas of quantum mechanics, because for how strange they are, I mean, they work. I mean, now today we are recording this podcast thanks to quantum mechanics. I mean, nothing of what we are using in this room could work if we wouldn't have the description that quantum theory gives us. Of course, if you want to understand then what is the reality, then you have to go into a possible interpretation of quantum mechanics. And we know there are different ones, like there is the first one was the Copenhagen interpretation, that is just this shut up and calculate. So it's like using this theory as an instrument, but there are other theories like, I don't know, many word interpretation that tells you that this superposition is just what we can see from the fact that there exist different possible universes, and like each possible outcome of the collapse, it's like the fact that the particle lives both in this green and yellow state is because there are two different possible universes, and when there is the collapse, we just fall into one. But I mean, we go a lot into philosophy now, so it's unfortunately, unless there is a lot of research on these foundational aspects of quantum mechanics, I mean, today we are not able yet to test none of these interpretations. So
we got one of the big topics you're working with.
Yes.
And then also you mentioned quantum entanglement earlier.
Yes.
How does that relate? Tell us a bit more about that.
I mean, entanglement is another very strange, if we want, aspect of quantum mechanics. And the fun thing is that at the time it was introduced in the theory as a way to sort of disprove it. So as a way to show that the theory was not correct, was not complete. Okay. If you want again to give a very naive definition of what entanglement is, I mean, I know, because otherwise we will go too far into math. If you want to give this interpretation, we can just say that entanglement is a sort of connection, a sort of link then we can create between quantum objects, and it's a link that we cannot explain in a classical way. So to make things more concrete, let's take always the particle that we have described before, this object that is green and yellow at the same time. But instead of taking one, now we take two of them. Now what we can do is that we can make these two particles interact and we can entangle them. And what does it mean? This means that we can create a connection between the two that is such that whenever we look at one of the particle and we make it collapse in green, for example, in this green color state, then the other one instantaneously and automatically also collapses into the green state. So whatever happens on one particle automatically and instantaneously happens also on the other one. That's entanglement. Where is the weird part? The weird part comes from the attack, because it's like the concept of entanglement was first introduced and studied by Albert Einstein. It was also a father of quantum theory, but also like during the last part of his his life, he was like, there is something wrong here. So Einstein, together with other two physicists, Podolsky and Rosen, said, okay, we can accept that entanglement is something that quantum theory is predicting, but now let's imagine that we have these two particles and we send them at the two far ends of the universe. Now, quantum theory is predicting entanglement, I can accept it, but then this means that if I go now to one end of the universe and I look at the particle and the particle collapses and becomes green, then instantaneously also the other particle on the other end of the universe collapses and becomes green. And according to Einstein, this was breaking any old laws of physics, and in particular the relativity principle that tells us that there is nothing that can travel at a speed that is faster than the speed of light. So if we have two events that are at the two ends of the universe, there is no way in which one can affect the other. And instead, what entanglement is telling you is that the collapse of the first particle on one end of the universe is actually causing the collapse of the second particle on the other end. So according to Einstein, this was an example for saying, look, like quantum mechanics has worked so far, but see, there is something wrong here. I mean, that's not, because like entanglement then, for how weird and how strange it is, it has been experimentally tested. Actually, the Nobel Prize in 2022, awarded to John Clauser, Anton Zeilinger, and Alena Spey, was exactly for the experimental test of entanglement. And it's fun because it has started as an attack to the theory, and today is considered as one of the most basic aspects of quantum mechanics.
Oh, so what I'm getting here is that the theory changes all the time.
I mean, it's not that the theory changes all the time. It's like, it's a bit how science works. It's like you want to explain a physical phenomenon, you want to explain something, and then you propose a theory for that. And that's exactly how quantum mechanics was born. But then this theory can have some implications. For example, entanglement was one of them. And, it's like in order to confirm the theory, then you have to be able to experimentally test all the possible implications that the theory has.
Definitely.
And this was one of the examples, that one of the biggest tests of the validity of quantum theory, actually.
And during your doctorate, are you testing different theories?
I mean, no, actually, during my doctorate, what I am doing is that I am exploring a little bit more the theory behind quantum entanglement, because like I just told you the example of two particles, and I have considered this very weird world in which we have only one characteristics with two possible colors. But we know that as the macroscopic world has more than just green and yellow, also the microscopic world is like that. And so like during my PhD, I've been exploring the entanglement in more, if you want, more realistic scenarios in which instead of having just two quantum objects, we have much more. So we have more quantum particles with more than just two characteristics. And what I've been working on was actually to be able to characterize entanglement in such systems.
Now we're speaking very limited numbers, two particles, three.
Yes.
But I imagine there's many, many more. How do you deal with such big numbers?
I mean, what do you mean, experimentally? Or because experimentally is a challenge that is still going on, because, it's like making the objects maintain their quantum nature is quite difficult. Theoretically, it's a matter of like combining mathematical tools and computational tools, because, it's like you perform some simulations, you have to deal with a lot of variables, and then from these simulations you extract the theory, and then you go back and forth. So
a big question that is going on is, how big is AI helping you in this? I imagine it's a big help when it comes to actual math.
I mean, actually, in my case, not at all. Because, there are some research paths now that are starting to grow in which they want to combine AI with quantum mechanics. I mean, personally, I think that we are quite in an early stage. So I think that most of the stuff that is going on right now is just for hype, okay? We still don't have a real connection between the two topics, but for sure, like at some point, given the power of AI, it's like at some point in the future we will get a lot of help from it, yes.
And so let's go back to your research and what you're doing right now. Is there anything you want to tell us that you've kind of found out, an aha moment during these 2 years that you...
I mean, there were a lot of aha moments because life as a PhD student, and I guess also as a researcher, is always a life in which, you go to the office and you have an open problem, like a question that you don't know how to solve. And then you go like that for like days, it's like you just struggle staring at the whiteboards, writing wrong stuff, erasing it, writing it again, and then at some point, like with this project that we had on entanglement, it was exactly like that. We didn't know what we were going to do. It's like me and my supervisor, we were working on this. And we started actually for an experimental question. It's like my supervisor had a collaboration with some experimentalists that wanted to detect entanglement in a 3-particle system. Okay. And we wanted to, derive the theory for this experiment. And only after that we realized, we can probably extend this and make a general framework, create a general mathematical theory. And I mean, that was a big haha, but we had multiple haha because because at some point we realized, oh, we have it. And then like we started working and I remember it was like before Christmas of the first year. So like I was going to leave like in 2 days. And then I was in my supervisor's office and we were just staring at whiteboard and realized, wait, we are wrong. We're like, and no, so that's not a haha moment. It's more like,
It's a roller coaster. You're going to go up.
Yes, up and down continuously. But then, okay, you fix it and then there is another haha moment. I mean, I can tell you like when I was leaving for the first Christmas holidays, I was like, because...
And I wanted to ask more practical. You said before, quantum physics allows us to have this microphone to speak to you. How is your research affecting the actual, like the material world we see around us?
I mean, like my work is more on the foundations of quantum mechanics. So it's more on understanding how these weird phenomena work. And then why there is a lot of interest on these weird phenomena is because of this second quantum revolution. I don't know if you have heard of it.
No, please tell us.
It's actually, so there is this big push now on this development of new technologies that use these weird aspects of quantum mechanics. So for example, like quantum cryptographic systems, quantum communication protocols, quantum computer, a lot. So like all the research that physicists around the world and physicists that work on quantum mechanics are doing today, it's all research that will be useful in the future because there is also a lot of work going on now on the development of these quantum technologies. I mean, one of the biggest goals is the building a quantum computer, a fully working quantum computer. And it's like all this work on understanding how quantum mechanics work, it's all useful for.
It's like a puzzle.
Exactly. It's like a puzzle in which you want to reconstruct a little bit how the microscopic world works. And the more you know, the better you are at using it for quantum technology.
Your PhD is creating one piece to fit in that.
Yeah, I mean, a very small piece. A very, very small piece, yes.
I wanted to ask, since we're nearing the end of our podcast, is there any advice you would like to give to someone who's interested, just like you were looking at your possibilities of even going into studying physics? What would you tell someone who's curious?
Yeah, I mean, it's tough. I mean, in the end, I'm still a PhD student, so I'm not probably the right person to give advice. But if I should, I mean, I would just say to enjoy. I mean, because it's like when you study at university, and I was among them, it's like you are always taken by, I have to do the exams, I have to pass the exams, I have to get a good grade, I have to go fast because, we are never on time. And sometimes, I mean, they are all important things, of course, but because for a career, it's important to be on time. But sometimes you have always to remember to enjoy what you are studying and do what you like. Exactly. It's like not caring so much about the grade, about what you're going to do in the future. Like enjoy what you are doing. If you are doing it because you like physics, then just enjoy.
That's so true. I can hear the passion also in your voice when you've explained all of your research, the topics. I feel like if you have it, you'll get there.
Yeah, exactly. I mean, no matter how difficult it is. I mean, I also struggled a lot during my years at university, but I mean, I liked it. So I was just spending all my days trying to solve integrals, understanding how it worked. So in the end, if you are passionate about it, you will definitely, get a degree, get a position.
How about any last advice on actually applying to Lund University as a PhD student?
Yeah, I mean, the important thing is really during your education, to use all the opportunities you have to at least try to do research. It's like, this is not possible everywhere, I know, but if you have some internship or something that is possible to apply to for having a little bit of experience on the research, that's really useful because it creates a better CV, let's say. And definitely, I mean, I would suggest all the PhD students, all the people that want to apply for a PhD to focus a lot on the cover letter. I mean, we are not just numbers, no? It's like we are humans. So even when you are applying for a PhD in physics, in science, you have to show why you want to do it. And you have to show to the person that is hiring you that, I mean, you are passionate about it. It's like, I'm coming there because I really want to learn these things. So these are the biggest advice that I would say give to someone that is going to apply soon.
Thank you. Thank you for your time today, and thank you for explaining more and making me understand what quantum physics, quantum mechanics is. Thank you so much.
Thank you very much for the invitation.
Thank you for listening to this episode of the Lund University International Podcast. If you're interested in learning more about Lund University, you can go to our website, lunduniversity.lu.se. You can also follow us on social media, on Instagram, Facebook, YouTube, and X. And you can connect with our amazing student ambassadors on Unibody. Don't forget to subscribe, and we look forward to bringing you a new episode very soon.